Hi folks, welcome back. In the previous video, we discussed about binary representation of integers in Python. So if you haven't watched that video, please do watch it once before watching this tutorial because understanding binary representation is fundamental to learn bitwise operators. Now, bitwise operators, they work only with integers. And as we discussed in the previous video, so Python uses 2's complement binary representation to store these integers, right? And these bitwise operators, they work at bit level of these integers. That's why the name bitwise operators. So we have these 6 bitwise operators. The first one is bitwise not. It is also called as ones complement, and it is represented with this symbol called tilde. The second one is bitwise or, which is represented with this vertical bar. Just above the enter key on your keyboard, you will find a key which has this slash, and on top you will have a vertical bar. So this is used for bitwise or. And next we have bitwise and, which is represented by ampersand operator. Next is bitwise XOR, which is represented by this cap symbol. And then we have shift operators, left shift operator and right shift operator, represented by two less than symbols and two greater than symbols. And in most of the real-time applications of bitwise operations, we generally use positive integers. So for the sake of simplicity, we'll only discuss how these bitwise operators work with positive integers. The first operator is bitwise not. It is also called ones complement. If you remember, we already discussed ones complement a little, in the previous video while we were computing two's complement, right? But let's just see this again. Ones complement or bitwise not is very simple. It's just the inversion of bits. That means you make zeros to ones and ones to zeros. Now let's take this example here. Here we have an integer 20 represented by this variable a. Now, if you try to convert this 20 to 2's complement binary representation, it will be 0, 1, 0, 1, 0, 0. We have seen how to convert decimal number to binary representation, that too in 2's complement representation in the previous video very clearly, right? So let's not discuss that again. And if you have any more doubts, please do watch it once again. So now we have this 20 binary representation. Now this bitwise not of 20 is nothing but you have to invert the bits. So 0 becomes 1, 1 becomes 0, right? In that way, you'll find all the other bits. Now, if we try to find the equivalent decimal value of this binary, which we got by doing bitwise not of 20, we compute this way, right? 1 into 2 power 0, 1 into 2 power 1 plus 0 into 2 square plus so on till minus 1 into 2 power 5. So if you compute that, you will get minus 21. Many people wrongly assume that bitwise not of an integer gives the negative value, but it is not correct. Here bitwise not of a, we got minus 21, right? Not minus 20. Now, in order to find this bitwise not, we have done all this calculation, right? Like first we had to convert this into 2's complement binary representation. Then we did ones complement, and then again we have to convert this back to decimal, right? But is there any other easier way to find the value of bitwise not? Actually, there is. If you remember, we have seen in the previous video that 2's complement of an integer will negate the integer. So which means that 2's complement of a, which means 20, will give you minus a, which is minus 20. And we have seen the 2's complement formula also, right? Which is nothing but 1's complement of a plus 1. So bitwise not or 1's complement are one and the same. So now in this simple equation, if you separate or if you solve this equation for 1's complement of a, you will get minus a. And if you send this 1 here, minus 1. So bitwise not of a or 1's complement of a is nothing but minus a minus 1. So if you take a value 20, it will be minus 20 minus 1, which is minus 21, which is exactly what we got. Now let's see the code for this example. This was the code example we have written during the previous video, right? So let me continue in the same file because this is also related to bitwise operators. I'll put a comment here, bitwise not, and here let me assign value 20 to variable a. Now let's try to print bitwise not of a, right? And one more thing also we can do is we can put a descriptive message like bitwise not. So writing these sort of descriptive messages help us analyze the output better, because you are going to print a lot of things and it will be very confusing, right? So it's always better to keep some descriptive messages, and comments are just for the sake of our own understanding, right? Like when we write a lot of code, things get really confusing, and having right comments will help us read the program better. So it's always recommended to use proper comments when we write real-time programs. Okay, now let's try to run this program. Let's right click, run bitwise operators. Now, if you see here, we got -21. And what if A is, let's say 45? What will be the output? So we know that bitwise not of A is -A -1. So now A is 45. So it will be -45 -1, which will be -46, right? So print of bitwise not of A. Now let's try to run this. As you can see, we got -46. So that's all about bitwise not. Now let's discuss about bitwise AND, bitwise OR, and bitwise XOR operators. So let's take an example to understand how these operators work. So here we have two integers 14 and 35 represented by variables a and b. Now, if you convert this 14 to 2's complement binary representation, it will be 0, 1, 1, 1, 0. We already discussed how to convert an integer to 2's complement representation, right? In the previous video. So now if you take 35, if you convert it into 2's complement binary representation, you will have 0, 1, 0, 0, 0, 1, 1. Now, as you can see here, the size of these binary numbers is different. Here it took 5 bits, here it is 7 bits. What we can do in that case is we can add leading zeros, which means on the left, to extend positive integers so that both the inputs occupy same number of bits. So here 14 is a positive integer, right? What we can do is, because this is smaller than 35, we can add leading zeros here. So if you do that, you will finally get A as 0, 0, 0, 1, 1, 1, 0, B as 0, 1, 0, 0, 0, 1, 1. And adding leading zeros will not change the value of this binary number. If you evaluate this, even this will give you 14. Here we are not discussing about negative integers, but in the case of negative integers, if you want to extend, instead of zeros, we will add leading ones. If you take an example, let's say 1, 0, 1, 0, which is actually -6, right? If you try to add a 1 on the left of it, and if you try to evaluate this, you will realize even this will be -6. Take a pen and paper and try to solve it. You will see that adding any number of ones on the left will still give you same value. Just remember that when you add new bits on the left, the last bit will get the negative weight. Now let's go back to our example. We have A and B with values 14 and 35. And these are the binary representations of 14 and 35. First, let's see how bitwise AND works between A and B. So these are binary representations of A and B, right? For 14 and 35, which we got. Now, when it comes to bitwise operators, they work at bit level, which means this AND operation is applied between these two bits and these two bits, and so on till the end of A and B. So if you take one bit from A and one bit from B, each one of them can be 0 or 1, right? So let's see the truth table for AND operation. Truth table is nothing but a summarization of the output for different combinations of input bits. Now let's assume X is a bit from A and Y is a bit from B. So what will be different combinations possible? Both of them can be zeros, both of them can be ones, or X can be 0, Y can be 1, or X can be 1, Y can be 0. Now, when it comes to AND operation, the output bit will be 1 for X and Y when both the bits are 1. In all the other cases, the output will be 0. So if you apply that for bitwise and between A and B. So as you can see, only in this case, we have both the bits from A and B as 1. In all the other positions, we don't have both ones, right? So we get zeros in all other positions. Now, if you try to evaluate this binary number, which means if you convert it to decimal using the same process, right? 0 into 2 power 0 plus 1 into 2 power 1 plus 0 into 2 cube, so on, the same procedure, you will get a value 2. Remember that when we give A value as 14, B value as 35, and when we try to find A and B while writing Python program, you will eventually get this final integer value, right? So all this binary representation is something that is used behind the scenes. That's why we need to know the whole process of how to convert integer to 2's complement binary representation and how to perform these operations at bit level to find out what will be the value. Now let's see bitwise OR represented by this A and vertical bar and then operator B. Now when it comes to the truth table of R, so the output bit will be 1 if at least one of the bits is 1. As you can see in these three cases, we have at least one bit as 1, right? So you'll get output as 1. In this case, when both bits are 0, then your output will be 0. Now, if you try to apply A or B for 14 and 35, so as you can see in these four positions, we have at least one bit as 1, right? So that's why we got output as 1. And in this position, we have both bits 0. That's why we got 0. Again, if you see here, we have at least 1, 1. So we'll get 1 here. And here we have both zeros. We get 0. Now, if we try to evaluate this binary number, which means if you convert to decimal, you will get 47. The next operator is bitwise XOR, represented by this cap symbol. Now let's see the truth table of XOR operation. So you can remember it simply this way. If the both input bits are same, your output will be 0. If they are different, the output will be 1. As you can see here, we have both input bits as 1. They are same. That's why we get 0. Here also both input bits are same, which are 0. So we'll get 0. In these two cases, both input bits are different. So we will get 1. Now if you try to apply bitwise XOR between A and B, as you can see here, here both bits are different, we get 1. Here both bits are same, right? So we'll get 0. And again, in these two cases, we have both bits are different, so we'll get 1. Here both bits are same, again we get 0. Here again both bits are different, we get 1. Here both bits are same, so we get 0. So we got 0 1 0 1 1 0 1. If you evaluate this, you will get 45. Now let's write some code for the example we discussed. Let's take A and assign value 14, and for B let's assign 35. Now let's try to print A and B and then A or B, and finally let's print A XOR B. And for better readability, right, when we have these kind of expressions, we can use spaces to separate the operands, right? We can give a space here so that the code is much more readable and it looks neat. All right. And let me also put a, descriptive message, right? Bitwise and or and XOR. Now let's try to run this code. If you see the output here now, we got A and B as 2, A or B as 47, and A XOR B we got 45. In this video, we discussed the first 4 operators. In the next video, let's discuss the remaining 2, which are shift operators. I'll see you there.